Hey everyone, in this video we're still talking about the graphs of our sine and our cosine functions, but now we're going to start talking about transforming our sine and cosine functions. And the type of transformations that we're going to perform on these trig functions are going to be like vertical stretches, compressions, and flips, horizontal stretches, compressions, and flips, as well as horizontal and vertical shifts. So in an earlier pre-calculus class, you probably saw how to perform these transformations to other functions. I want to start by just a general review of these basic transformations. So we'll talk about how to do a general stretch, compression, shift, or flip to any function, and then we'll look at doing it for our special sine and cosine functions. So we have quite a few transformations to get through. I want to start with shifts because they are essentially one of the simpler transformations. All right, so there's two types of shifts that we want to talk about here, and they are vertical and horizontal shifts. And so there's kind of a common setup that we refer to when describing these transformations. So the transformed function is the function we are calling g, or g of x, and we're going to think of that as a transformation of a more basic or already known function, f of x. So for our basic sine and cosine functions, they will be playing the role of f of x. And depending on what kind of transformation or shift in these examples that we're performing to sine or cosine, that'll give us our new function g of x. And so the thing to remember for these shifts is shifts are going to correspond to some kind of addition or subtraction happening inside the equation of our original function. And depending on where that addition or subtraction takes place, will determine what kind of shift occurs. So remember, if we think about our function notation, f of x is like our output or our y value. So in this initial shift at the top one here, we have some y value that's having this number d added or subtracted to it. And so that's going to affect only the y values for the graphs of our function. And so that's going to correspond to a vertical shift. If that number or constant d that we're adding on is a positive number, then our graph's going to go up d units. And if that number d is a negative number, then it'll go down d units, or in this notation, the absolute value of d units, because we don't really say something goes down -2 units. We just say it goes down 2 units. So the other type of shift that can happen is a horizontal shift, and that's going to correspond to addition or subtraction that occurs in the inside of our function for this function notation. So it actually doesn't really matter if you write this so much as x minus c or x plus c. The thing to remember here for these horizontal shifts is that it is always kind of counterintuitive. So if we have f of x minus c, then the graph of g, our transformed function, is just going to be thought of as a transformation of our original function f that's been horizontally shifted c units. It'll be right if c is a positive number, and so that would look like x minus, like 5, that'd be shifted to the right 5. And if c is a negative number, like that was x minus -5, that actually look like x plus 5, and it would shift to the left. The thing to remember about these horizontal shifts, and this is actually true of all of our horizontal transformations, is they're counterintuitive and essentially do the exact opposite of what it kind of looks like they might do. So if we have something like x plus 4, you might think, well, we're adding 4 to that x value, it shifts it to the right 4, but in reality, it does the opposite and actually shifts it to the left 4. That's usually covered when transformations are first discussed, but let me give you a quick little recap of why that is the case and specialized for our sine and cosine functions. So to refresh our understanding of why this kind of counterintuitive thing occurs with these horizontal shifts, or in general horizontal transformations, I want us to think about comparing sine of x to sine of the quantity x plus 3. Here our addition or subtraction is happening inside of our function, inside of these parentheses. That's how we identify it as a horizontal shift. If the parentheses ended and that was a plus 3 outside, then it'd be a vertical shift instead. But getting back to the point here, how can we tell that this is actually a shift to the left 3 instead of a shift to the right 3? The key thing to think about here is the domain of our sine function, right? Normally our sine function has that domain of all real numbers, right? That is the domain, it's everything. But if we wanted to graph just say that first period of our sine function that we looked at, we have to input all the x values from 0 to 2 pi. So our sine function, whenever it inputs the interval of values from 0 to 2 pi, it's going to output that one period that starts at 0, goes up, goes all the way down to -1, and comes back up to 0. Now, if we compare that to sine of x plus 3, this is still our sine function we're talking about. The only thing is the input has changed. Our input is now x plus 3 instead of x, but the same fact is going to be true about our input, in that in order for our sine function to output one of its periods, its input still has to go through this interval from 0 to 2 pi. Well, now our input is x plus 3, so this strange new quantity, x plus 3, has to go from 0 to 2 pi in order to spit out that one period that we were looking for. But what do the values of x itself have to go through in order for the quantity, the new input x plus 3, to go through this interval of values? Well, we can solve this quantity for x to figure that out, and that's where we see why our horizontal shifts are sort of counterintuitive. In order to solve this inequality, to figure out the x values, we actually need to input into this transformed version to get the same outputs as our original version. We had to subtract 3 from all 3 sides of our inequality, kind of undo that operation that was happening inside of our function, and the inverse of adding 3 is subtracting 3. So in reality, we had to actually shift everything to the left 3 to make up for that plus 3 in the inside of our function. That's some algebraic reasoning for why these horizontal shifts are counterintuitive. You definitely don't have to go through that every single time. The key thing to remember is it's always opposite or counterintuitive of what's happening inside of those parentheses. All right, so we just covered our first set of transformations, our shifts, both our vertical as well as our horizontal shifts, and we saw that those corresponded to addition or subtraction, depending on whether that addition or subtraction happened outside of our function or inside of our function, can help us determine whether that is a vertical or horizontal shift. Our next set of transformations, the last set, are stretches, compressions, and flips, and they're all going to be done together, and they are going to be the transformations that correspond to multiplication or division. All right, so I've gone ahead and wrote up some important review notes for these other sets of transformations, our stretches, compressions, and flips. And one of the key things to remember about these transformations is that they correspond to multiplication or division. And similar to our other shift type of transformations, whether that multiplication or division happens outside or inside of our function will determine whether it is going to be a vertical or a horizontal stretch, compression, or flip. So in this first one we describe, we say g of x, our transformed function, can be written as some constant multiple of our starting function f of x. If we can write it in this form, then the graph of g is going to be the graph of f that has been vertically stretched, compressed, or flipped. And whether it is going to be a vertical stretch, compression, or flip will be determined by that number a that we are multiplying the outside of our function by. So if that is a large number, and by large we mean bigger than 1 in absolute value, then that's going to vertically stretch the graph of our function. Again, think of f of x as y values. We're just multiplying all of our y values by a. If a is bigger than 1, our y values get bigger, and that causes a vertical stretch. If the absolute value of a is less than 1, so we're multiplying by some small number, like a small fraction, that's going to cause our y values to shrink and cause a vertical compression. And if a is negative or less than 0, that's going to cause our y values to flip over the x-axis. So we will get a vertical flip, and we might also have a stretch or a compression, depending on if that's like -2 or -1/3. If it's -1, then we only have the vertical flip. But if it's any other negative number, we'll have a vertical flip along with some stretch or compression. So a very similar set of notes for our horizontal stretches, compressions, and flips. So now our kind of function notation is if we can write our function g of x as some starting function f, not evaluated at f, but at b times x, so we've multiplied the inside of our function by this constant number b, then we know the graph of g is going to be a transformation of that starting function f, and it's going to be a horizontal transformation. It'll either be a horizontal stretch, compression, or a flip. And again, that's all going to be determined by that special number b. And just like what we saw with our horizontal shifts, our horizontal stretches, compressions, and flips are going to be counterintuitive as well. So what I mean by this being kind of a counterintuitive set of transformations here is if b were a number that is larger than 1, like 5, just a quick glance and using our intuition, we might think, well, we're multiplying our x values by 5. That's going to stretch them. That's kind of the line of reasoning that we used up here, right? But it doesn't actually work that way. If we multiply by a number b that is bigger than 1, that's actually going to cause a horizontal compression. So now if we multiply by a small number, that actually causes our function to horizontally stretch and become wider. And similarly, if b is negative, then we're just going to have a combination of a flip along with a stretch or compression. Unless b is -1, then we will only have a flip. And that's a horizontal flip instead of a vertical flip. Recall in our little reminder for why the horizontal shifts work counterintuitively, we can use that exact same line of reasoning or argument to show that our horizontal stretches, compressions, and flips also happen counterintuitively. So over here, normally we think of sine of x, right? We have to have the inputs go from 0 to 2 pi. Well, now if we had something more general, like sine of bx, well, now we need the inputs to still go from 0 to 2 pi if we want to generate one period of our sine function, which is what we usually want to do when we are graphing. But now x itself has to go through a different set of values. To find that interval of values that x itself has to go through, we have to divide all three sides of this inequality by b. 0 divided by b is still 0. B times x divided by b simplifies to just x. We cancel that b out. And 2 pi divided by b simplifies to, well, 2 pi over b. We have to know more about b to rewrite that in any other way. But the point here is, normally our sine function had to go from the interval from 0 to 2 pi to graph one period. Now our sine function would have to go from the interval from 0 to 2 pi over b. So if b is bigger than 1, then this is going to turn this into a smaller interval than what we started with. And if b is smaller than 1, that's going to cause this to become a larger interval than what we started with. So when we say over here that we have like a horizontal compression, we usually want to describe that compression factor, and that'll be 1 over b, or the absolute value of b. Same thing for stretching, right? So if we have like sine of 1/2 times x, we wouldn't say that we have a horizontal stretch by 1/2, because that description makes it sound like we are shrinking the sine function's domain. Really, we have a horizontal stretch by 1 over 1/2. 1 over 1/2, though, is just a really complicated way of saying 2, and that makes more sense. If we have sine of 1/2 x, that is a horizontal stretch by a factor of 2. That's the transformation that is actually occurring. So in general, if we have f of b times x, that's going to be a horizontal stretch or compression depending on b, and that stretch or compression factor is not b itself, but the reciprocal 1 over b. So just a quick little recap before we look at some examples of applying these basic transformations to our sine and cosine function. A couple things to remember to keep all this straight. Shifts correspond to addition or subtraction. Stretches, compressions, and flips correspond to multiplication or division. Now, how do we determine if it's going to be a vertical or horizontal shift, or a vertical or horizontal stretch, compression, or flip? That all depends on where that addition or subtraction or multiplication and division occurs. All right, so if our addition or subtraction or multiplication or division happens to the outside of our function, that's always going to correspond to some kind of vertical transformation. If our addition or subtraction or multiplication or division happens inside of our function, that's always going to correspond to a horizontal transformation. And remember, when we have a horizontal transformation, it's always working counterintuitive to how you might expect. So if we had x plus pi, it actually shifts to the left pi. If we had f of 4x, that doesn't stretch it by 4, it actually shrinks it by 1/4. So one last thing to note that we'll see how to do in some upcoming examples is to how to actually use this information to perform our transformations. So from looking at the equation of our transform function, we should be able to identify whether it is a shift or a stretch or a compression, and whether it's happening horizontally or vertically. From the graph of the original function, we'll be able to highlight some key points that we can use to re-sketch our graph. Then what we're going to do is transform those key points. So say we had a vertical shift, then we just look at those key points and change the y values depending on exactly what our vertical shift was. If we had a horizontal shift, we have to change the x values by adding or subtracting to them depending on our horizontal shift. And if we had stretches, compressions, or flips, we'd have to multiply those y or those x values by the correct number, depending on exactly what type of stretch, compression, or flip is occurring.